Hi gang, Mr. G here, and today we're going to talk a little bit about geometry. I know, but this is a really cool geometry lesson, and it plays into some of the decisions we're going to be making here on this bowl, this barrel, and where the notes are going to be, because the next step I have to do is to scribe out where all of the notes are going to be. And I've already done it around the edge, and I'll show you that next time. But these middle notes, the stuff in the middle, they're kind of different little process that we go through for that. And so I want to take a moment out and talk to you about this geometry. Now, you've seen me obsessing on how deep I'm sinking this pan. And it is an important decision because every time I sink the pan a little bit deeper, I gain a little bit more surface area, or what I like to call real estate. As I do that, though, I'm actually making the instrument harder to play because there's more reaching in and more severe angles on the sides, as opposed to more flat playing, which you can usually play a little faster if it's flatter. And I'm also increasing the risk that that one errant hammer blow that splits this thing open, because I am making the metal thinner and thinner as I sink this instrument deeper and deeper. But I was really curious, really just exactly how much surface area am I giving up by not going as deep as Snowflake here. Now, Snowflake is sunk to a depth of 8¼ inches, and we are at 7.5, or just a little less than 7.5 inches on this. And I'm going to call it 7.4 inches just to make it fit into calculations the right way. If you look at the inside of this pan, and you compare it with Betsy over there, you'll see that Snowflake, the more modern and deeper pan, has a lot more room between the notes. Those notes are actually the same size as the notes on Betsy, but there's more room between them. And this gives you a cleaner sound out of the high notes. And I actually have one extra note in Snowflake here, this high F, that I don't have on Betsy. And so, with the more surface area, you can actually get more notes and more space and more clarity and a cleaner sound, but it is harder to play and there's higher risk of splitting it open. So that's the trade-off. And I have decided to go very conservative, and I'm not trying to make a professional level modern pan. I'm trying to make a pan that sounds just a little bit older. So I wanted to know how much surface area I'm giving up by not going this deep. And so we're going to talk about the geometry that's involved with that. And the unit of measurement we're going to use is the square inch. So we're going to use the things that we do know to find out the things we don't know using geometry. And here are the things that we do know. We do know that this barrel, the inside diameter of this barrel here, is 22¼ inches, and so is this. These are both oil barrels, so they've got very similar dimensions. So our inner diameter is 22¼ which means that our inner radius, the radius, is half of that, which is 11 1/8 of an inch, or 11.125 inches. That's a known thing that we have, thanks to this. Now then, we also know how deep we sunk this. This is sunk to a depth of 7.4 inches. This one is sunk to a depth of 8.25 inches. Now, if this instrument here, this barrel, had been sunk down to the same depth as the radius, then what we would have created is exactly half of a sphere, right? So if you assume that this is, just imagine that this is down 11.125 inches, and the radius is 11.125 inches. That would mean it's exactly half a sphere. And that would be easy, because you can calculate the surface area of a full sphere. It's the radius squared times pi times 4, or 4 pi r squared. And then we would just divide that in half, and that would tell us what our surface area is. But we didn't sink this thing down to 11 1/8 of an inch. And so we have a different sphere that we're working with here. And by completing the rest of that sphere, we can begin to calculate how much surface area is in here. Imagine the full sphere. And the center point of that sphere would actually be higher than the rim of this drum. Then we would have the center point of a full sphere. And that sphere would come out of here, and the sides would actually be about an inch wider on each side. I did these calculations. It would be 12.06 inches would be the actual radius of the sphere that this bowl is a part of. So now you can imagine that my hands are on exactly opposite sides of a sphere, and that's the sphere that we would have if this was complete. When you take a sphere and you slice a plane through it, you get what's called a spherical cap. And in our case, the plane is the plane created by the top of the rim of the barrel here. Just imagine a big tabletop. That's our plane, and we have sliced right through our sphere here, and we create what's called a spherical cap. And it kind of helps to imagine this whole thing upside down, because then it has the shape of a cap, right? And the geometric terms are going to use that terminology, and so it's a little easier to visualize if you kind of flip it upside down in your mind. So the spherical cap is created by slicing the sphere with a plane. The circle that results from that slicing, this circle here, is called the base of the cap. And so if we flip this upside down and make it sort of a little dome, then the base of the cap would be the circle that the dome sits on top of. It's different than the radius or the diameter of the full sphere, right? So we know that the base of our cap is 11.125 inches in this case. The radius of this base is indicated with a lowercase r, and the depth of our sink is actually referred to as height, represented by a lowercase h. Remember, if this was upside down, it would be height from the base, right? So we're just going to replace the word depth with the word height here. So the formula to calculate the area of a spherical cap is this. Pi times radius of the base cap squared plus height of the cap squared. So in this case, the radius is 11.125 times itself, or 123.76. And h squared, or the height squared, is 7.4 times itself, or 54.76. And if you add those together, it comes to 178.52. And if we multiply that times pi, we get 560.84. So the surface area of our bowl is 560.84 square inches. 560.84 of these can fit inside of this bowl. But of course, the bottom line is, how much surface area am I giving up by not sinking the extra 3/4 of an inch? I'd like to know what the difference is if I just go a little bit deeper. Well, I calculated the surface area of Snowflake here, and came up with 602.65 square inches for that surface area. And again, ours is 560.85 square inches, and the difference is 41.8 square inches, or this. This is the difference of surface area between sinking a pan to a depth of 8 1/4 inches as opposed to 7 1/2 inches. And there's a little more area there than I thought. It's about 6 1/2 inches square. And I could easily fit in quite a few, little notes into that. But again, this really represents the area between notes that I'm going to have to sacrifice. So I'll have to squeeze some things in order to get all this stuff to fit. And I am going to compromise some of that clarity of the tone for this. But again, I'm not trying to make a recording instrument. I'm just trying to make a nice vintage pan that's got some projection on it and that I can just play and have some fun with. And it's easy to play. So next time I'm going to show you how I have marked the notes in here and what the next step of the process is after that. This is a very important step, deciding where the notes are going to be and making sure that they're the right size. So we'll talk about that next time. And until we get to then, well, I'll just say stay safe and ciao.